Okay.
Hello everyone, welcome back to the Cauchy seminar in differential algebra. We are very happy to welcome today Khalil Ghorbal from INRIA France, who will give us the presentation today on proving the non-existence of Darboux polynomials.
Thank you. Thank you, Daniel. Thank you for having me again. So this is my second Cauchy seminar. I think the last one was 4 years ago about invariant sets and so characterizing invariant sets, if I remember correctly. Thank you everybody for attending. Feel free to stop me whenever you want. I'll try to go or to start slow. Maybe some drawing some pictures on my slides to make things clearer. Nevertheless, just feel free to stop or write down messages. I'll try to read them and answer them. It's better to make it interactive. So today's talk is about the non-existence of Darboux polynomials. Of course, I'll define what they are. This is joint work. I've been working on this now for maybe 4 years or so. It's a joint work with Maxime Bridoux. He was a PhD student with me. He defended his thesis last year at INRIA, France. And he's now teaching at École Préparatoire also in Paris. So I'll start this talk with, before actually introducing formally what Darboux polynomials are. Probably you know what they are. I've seen some of the audience definitely know what Darboux polynomials are, but I'll start with a simple example from physics to just motivate the need for proving sometimes non-existence instead of actually finding these objects. So this is an actual picture or a photograph rather of the sun, of our sun. So it's the star, the closest star we have here. And I'm not gonna talk about this the black spot of the sun, but rather at those nice polygonal regions here over. So I can draw actually. Let's see if I can draw. Yeah, I can draw. So you see those shapes here, those nice shapes all over the surface of the sun. So physicists are trying to explain where these are coming from. And so let's say the most common hypothesis is this is related to what's called turbulence or convections. It's actually simple. You can think of it, you have your pan on your stove, you're heating it from above. And when there is a difference in the temperature between the surface, let's say the water or any liquid, so there is a difference in the temperature between the surface and the bottom, the liquid starts to move. And it moves in a funny way. So it does like, those nice circles going upwards. And so the idea is to say, well, what we are seeing here on the surface of the sun is exactly this. This picture here shows that when the convection is starting, it forms what's called sails on the surface, and this is what we are observing here. Of course, physicists are very good at trying to model this in the simplest way possible, obviously, if possible, if that's an option, and reproduce this experimentally. And actually, we can do this. So this is a lab experiment showing what appears to be actually. So this is a liquid. It's heated up from, let's say it's a cross section of liquid to see what's happening. It's heated up from below, and we can see actually this sort of let's say a mushroom forming here. So this is one of the mushroom, and maybe this is the other side of it. And as the caption says, there is a cooler region. So the cooler region appears in brown, so it's in kind of inverted, and the warmer regions appear in green and blue. And we can sort of see those cells appearing if we reproduce this experiment in the lab. And there are actually models, rather simple, which actually model this. I'm going to show one model just in a few slides. So Physicists, of course, are interested on those kind of systems for different reasons, one of which I just mentioned just earlier. And in particular, we try to have like simple models, as I said. So one of these model is called it's by Shimizu and Morioka. This is a paper in by 1980, and the model is like so. So it's close to Lorenz model. If you probably heard about, this Lorenz model of the butterfly effect and the strange attractor. This is quite similar to the Lorenz model, but actually more, let's say, it gives more satisfying results for turbulent convection. So when the Rayleigh coefficient is high, whatever those are physics. Let's say parameters, but this model makes more sense to explain the phenomenon I just showed. This is, let's say, to keep in mind. As you can see here, it's an what's called an ODE, ordinary differential equation. We have three parameters, x, y, and z. I won't be giving the physical meanings of what's x, what's y, and what's z. And there are some parameters. So here we can observe, for instance, we can see that there is lambda as a parameter. There is also an alpha here as a parameter, and the system is almost linear. It's not quite linear because, of course, we do have those monomials. Let's say like xz in here and x square in here. Okay, so this is a parameterized model. It's called Shimizu Morioka. It's presented by the two authors in the 1980. And once we have such systems, physicists ask themselves whether they have integrals, whether like polynomial integrals, rational integrals. So those are functions that are constant when time moves. And the idea behind is those functions encode some sort of, let's say, energy functions. So this is an important question. Integrability is an important question when it comes to, let's say, theoretically study a model, modeling a physical system like the one we do have here. So in the literature, so yeah, this is just I reproduce it. So I take this model, Shimizu Morioka model. I just put it in Mathematica, and I draw the stream plot, what's called stream plot. So this is the vector field. I won't be able to reproduce, sorry, the experiment, I mean the drawing here. What's nice is that this particular one is for two specific parameters of alpha and lambda that you can see on the bottom of your screen. If I manage probably to make it to remove, let's see if I can remove this, or maybe zoom in. Yeah. So this is for alpha 0.45 and lambda 0.75. And you can see sort of strange attractor like in Lorenz models. And what could be nice actually to try if you have means to draw those stream plots, if you move slightly alpha, let's say less than 0.4 or lambda greater than 0.7, this attractor actually will change form. So the system is definitely bifurcating. It has different behavior. The behavior is different.
Khalil,
Yeah,
I apologize for asking a question.
please
So
don't. It's
the
good. Go ahead.
integrability factors are well known for the planar systems. So this is what you use to solve the problems. So the question is what you call uh, the Darboux factors for the 3D systems that, as you understand, can simplify your analysis of the 3D dynamical system.
So yeah, it can, yeah, although I did not yet define what Darboux polynomials are, those factors or those Darboux polynomials can indeed simplify the dynamics we're studying and can also be used to find or to compute rational invariant functions. So on both ends, this is called like the Darboux integrability, and those let's say those pieces, those polynomials do play a role. So we know, for instance, that the system has a rational invariant function if and only if it has Darboux polynomials. So if we manage, for instance, to prove their non-existence, we do know that the system has no rational invariant function. And they're not necessarily themselves invariant polynomial functions, except special cases. But they do play a role in either simplifying the system, as you just said, as you just mentioned, or finding rational invariant functions, which are also important in the integrability theory. I don't know if I'm answering correctly the question, but I do confirm that Darboux polynomials do play a role in integrability.
Yes. Well, I'm waiting for your
Though the definition, yeah, it's
continuation.
coming, it's coming. Yeah, I won't make it longer. So this is a paper. This is a more recent paper. The model, we do know the model from the 80s, 1980. And this is a more recent paper about the integrability analysis of Shimizu-Morioka system. And those are two excerpts from that for this same paper. So one section of the paper is try to find all polynomials, rational first integrals of the Shimizu-Morioka system with the help of Darboux theory of integrability. Okay, whatever that is, I'm coming to it. And then in section 4, the author says, we show that the system of interest here, when alpha is different from 0, so recall alpha here is a parameter of the model. So this alpha here is a parameter of the model, is rationally non-integrable, okay? But for in the sense, well, whatever, in the sense of the parameter values, etc., etc. So what's interesting here is that one remark came after. We conjecture that the Shimizu-Morioka model has no Darboux polynomial when alpha is equal 0. So the authors basically do study this the system for the particular parameter alpha and 0. And if you just go ahead and read the paper, or even actually you go through the paper, let's say it's cumbersome to prove the non-existence of Darboux polynomials, and they leave it open for alpha equals 0 because it actually requires like the same analysis again for the parameter alpha is equal 0. Okay. So one of the examples I'm going to talk about today, after presenting how we are going, or one way to automatically reason about Darboux polynomials, is that we solve this conjecture and we actually show that the system has no Darboux polynomials for any valuation of the parameters alpha and lambda. And the analysis I will be carrying out is actually insensitive in some sense, or actually can handle properly those parameters, of course, at the cost of some extra computations. Okay, so this is like the overall context with just an example or an appetizer, let's say, to motivate the need for those Darboux polynomials, in the sense that they're not just let's say abstract algebraic objects that mathematicians are interested in. They do have in practice, they are useful in practice, let's say. Okay, so coming to what Darboux polynomials are. So this is a very the basic definition of Darboux polynomials. They are quite simple objects. They have been studied since the the end of the 19th century by a guy called Gaston Darboux. This is where the name comes from. It's not the only name in the literature. We can find eigenpolynomials, for instance, for those objects. And the reason will become obvious. So we are given a polynomial derivation. You can see this or read it as an ordinary differential equation with the right-hand side being polynomials. So those f1, f2, all the way to fn. So those are polynomials. You can fix a field, and this is going to be, these are going to be polynomials. So this is why we call this a polynomial derivation, okay? So we are given this. This derivation is given, and the polynomial P is called Darboux. Of course, it's not just Darboux in general, it's Darboux for the fixed derivation we have. If and only if it satisfies a very simple condition. So the derivative of P, so here d of P, sometimes it's called P dot because, of course, in physics, this Newton dot notation means the derivative with respect to time. And in the context of differential algebra, we don't really care. Is actually equal to some other polynomial Q, which is called the cofactor, multiply the polynomial itself. So if you like, we can write down this as the derivative of P. Let me maybe write it down differently. Probably change the color to make it more. So yeah, so what we are asking here is that the derivative of the polynomial P is included in the ideal generated by P. So this is notation for the ideal or the principal ideal, let's say generated by P more precisely. Another way to say the same thing is that this principal ideal generated by P here is a differential ideal with respect to the derivation we are playing with in our case, okay? So these are equivalent definitions. We are given a derivation, a polynomial derivation. You can write it as you can write it as a form of an ODE. You can also write it down sometimes also like the sum of fi and di. So this is like an operator-like definition or representation. And we are asking whether such polynomials exist. Okay.
I think there's a question. Sorry.
Yeah. Sorry. Go ahead. Yeah. It's important actually to understand the definition. So yeah, please stop me if I'm not clear here.
Can you hear me?
Yeah, I do.
Okay. So I just wanted to ask before you go on further. Maybe you said it, but I don't actually get. So the point how you started was like, okay, let's look at why it's important that Darboux polynomials like don't exist as a solution. So you started with the system and how applied, like in the applied world, it means what it means. So for the system, what Shimizu Morioka,
Yeah.
so if the Darboux polynomials are not solutions because of the theory they use, will it mean that there are no solutions and that's why it's important? Like, why is it exactly important, and what does it imply for the system that that you had the graph and simulation of? Like, what does it actually imply for the real life situation you came from?
Okay. Yeah, so the non-existence of Darboux polynomials doesn't necessarily mean that the system is, I mean, this is an ODE, first of all, this is an ODE with a polynomial right-hand side. So for any initial condition, at least locally, we know that there exists a unique solution, right? So it's what we are interested in. So it's not necessarily the existence of the solution of the ODE we're playing with that matters, but rather two things, let's say. The first one is we're trying to understand what sort of invariant the system has. So by invariant, I mean here, so if we switch geometrically speaking, we are interested in finding, for instance, like hypersurfaces that are invariant or that are kept invariant by the dynamics. So we're not necessarily trying to solve, we're trying to find out whether there are hypersurfaces that are invariants. This is one interest of finding or non-finding Darboux polynomials. The other one is the existence, as I said, of invariant rational functions, which is again, so it's an invariant analysis of the ODE. So we're not necessarily interested in solving the system or numerically solving the ODE, the differential equation, but rather trying to find out whether it has some invariance that goes with it. Why? Because those invariants do capture an interesting physical properties that physicists who have these models are interested in.
I see. Okay, so if Darboux polynomials were not invariant,
Yeah, so they are not
under the
invariant, but
system, it will mean something for the simulation you are making. You will not observe a certain phenomena, shape, or something appearing.
yes, yes. But the other thing important actually is that although p itself is not an invariant function as a polynomial, the set of zeros of p is always an invariant. So if p is a Darboux polynomial, then p equals 0. So all the points, let's say px equals 0 to make it maybe more precise. So px1, x2, all the way to xn. So the zero sets of the polynomial p defines an invariant region of the space, always. So if
So
an
may I allow to interfere? So, Khalil, you extend the definition of the Darboux integral function by saying that it is a vector, a polynomial that satisfies not just by one scalar identity, but several identities, because your system is multidimensional.
Yeah, the system is multidimensional. The cofactor q is a polynomial. It's not a scalar. I'm not really extending per se because the definition, well, I mean, Darboux gave the definition for
No, this just from a naive point of view means that your Darboux polynomial factors are much scarcer because they need to satisfy not just one but several identities.
Yeah, that's a good intuition. Actually, they are rather scarce. They are rather rare. Actually, in general, if you just pick up a random polynomial derivation, it's unlikely that the derivation has a Darboux polynomial. Because yeah, they
So
do
you're
satisfy the three
studying
constraints.
a really very rare beasts in the uh, realm of multidimensional. Multi means that's more than two
Two, yeah.
of the dynamical systems.
That's right. Yeah. They're rather rare beasts. So actually, this is a good intuition and a good observation. So one may ask actually, since those objects are rather rare, we might probably need. It's actually better to try to prove their non-existence instead of just trying to finding them. This is actually one motivation of finding means to prove their non-existence. Yeah, that's correct.
No, don't take me wrong. So whenever you find some things, is great, but once we see that you are chasing a rare beast, then this claim that there are no such rare beasts is a little bit more easy to accept.
Okay, it's a little bit more easy to accept. Okay, I see. Okay, so for Seda, did I answer your question regarding the so as just to finish so although P itself is not invariant as a function, its zero set is invariant. So this is nice because you know there might be, for instance, limiting cycle that you are interested in. And if those limiting cycles are algebraic, actually they're likely to be Darboux polynomials or related to Darboux polynomials. And this is something interesting to answer.
Thank you.
Excellent. Okay, so we are all on page of what Darboux polynomials are. And so the task here, what I'm going to be interested at is I am given the derivation, the polynomial derivation, and I'm trying to reason or to try to not necessarily find them, but prove their non-existence. So what do we have at the state of the art? So this is kind of a really big picture. I'm not being exhaustive. I'll really be just jumping to give you some sort of what exists out there. Oftentimes, we do see in the literature, even now, papers devoted to proving the non-existence of those polynomials for one particular system. I just showed a paper from 2020. We do actually have more recent papers that are interested in the non-existence of Darboux polynomials. There are geometric approaches based on singularity theory because oftentimes, actually, the zero set of Darboux polynomials goes through singularities of the derivation we are interested in for good reasons. There are also some more other approach, more algebraic. For instance, there is what's called the ecstatic method. I will not present it here, but the waving hand, the idea is that it computes one big polynomial as a determinant of one big matrix, and the factors of this determinants, or actually Darboux polynomials of the given derivation, are factors of this big polynomial. This is the ecstatic method. There is also a more straightforward way to go, and this has been investigated over and over again by many authors. There is Jacques Arthur Vail. Actually, I think even in the Singer procedure, this is how things are implemented in a computer. We fix a total degree bound, well, let's call D. For instance, you say, okay, I'm interested in quadratic Darboux polynomials or cubic Darboux polynomials. You represent the polynomial as an ansatz. So by ansatz, I mean the coefficients are unknown, or they're left as undetermined. And you compute what's called the normal form of the derivation of P with respect to P. So this actually means really it's the remainder. So you basically do compute the quotient or the remainder of the quotient of the derivation of P, which is a polynomial, over the polynomial P itself. And then you solve for this normal form to vanish. So this actually gives you a big polynomial system and the coefficients of the ansatz P. And if you're lucky, if you have a solver, if you have enough time and enough memory, then you'll be able to say, well, there exists a solution and you'll be able to find it, or there is none. And you will just conclude that there are no Darboux polynomials up to degree whatever you fixed. Linear, quadratic, cubic, whatever, okay? This is how most computer systems that compute Darboux polynomials actually work. Now, the problem here, there are many problems, right? One is you need to fix the degree D, because otherwise you will not have polynomials, and this is, I mean, you need to represent those objects on a computer. The second is, and the most important one actually, is that the system you need to solve becomes very large very quickly, and there is no clear algebraic structure behind the system that one has to solve in order to exploit it. So basically, you give this to let's say a Grobner basis computation or whatever you have at hand, and you cross your fingers and wait. So this has been limited so far, and even with our experiments more recently, to let's say planar or cubic systems, so degree 3 systems, so n equal 2, n equal 3, n being the dimension of the system, with a degree bound of 3, maybe 4 or 5. Okay, for very, very small systems, we can maybe, go all the way to degree 9, 10, but that's it. Because the system to solve becomes very, very large. And moreover, this idea does not allow one to prove that those objects do not exist, because you need to fix the bound. So what I'm going to present next is one way to actually try to extend this rather simple method of direct computation to prove the non-existence, if possible. And this is what's going to be the next part of the talk. So one main concept of we've been introducing, we've introduced and we've been playing with over the past 40 years is what we now call formal polynomials. So those are polynomials where the total degree D So I'll start with, shoot, I just jumped. So I'll start with, uh, um, what can I say? So D here, what's important to keep in mind with respect to a standard monomial to make the difference between what I call, so I start with what I call a formal monomial. Okay, so this is a formal monomial here, compared with a monomial, is that the degree or the total, the multi-degree D here is unknown. Let's say it's a symbol. Okay. So in general, a polynomial has the form, let's say x1 square x2 cube. Okay, so we do know those exponents, and this is why, for instance, we need to fix sometimes the total degree if you want to play with these objects. We've made the idea, which might seem rather bold, is okay. What if we keep the exponent symbolic? It's just some indeterminate. It's called multi-degree. It's D. It's D1 all the way to Dn. We know nothing about it, and we call those objects formal monomials. Okay. Now we added some gamma here, and we just require gamma to be in Zn. So basically, what I'm saying is, I'm allowing myself to play with monomials of the form, let's say x1 d1 minus 2, x2 d2 plus 1, let's say. Okay, so this is what's called a formal monomial. You might ask, what's d1, d2? I don't know. They're just undetermined, and that's it. Okay. Now, formal polynomial is just a sum of formal monomials, of course, with some coefficients here. Okay, living in some field. Could be undetermined as well if we are playing with ansatz, but we fix a field otherwise, and we have those coefficients. Now, a formal polynomial does not have a finite support, because here finite is not necessarily well-defined. Again, because this multi-degree D is not fixed. It's itself an undetermined. Okay? And I'm summing here, so it's an infinite sum over some set, this gamma D, and this gamma D is it is a subset of Zn, satisfying two conditions. And you might actually notice the slight difference between this here and this greater than or equal here. So I will start by explaining why these are. So the simple one is this one here. So this is component-wise. This actually says that basically that gamma 1 plus d1 is greater, so it's component-wise, and gamma 2 plus d2 is greater than or equal 0. Okay. The first one, this one here, it's a monomial ordering. Okay. It's a monomial ordering because although I did not say it so far, but as soon as you start doing polynomial reductions in the multivariate case, you need to fix a monomial ordering to perform the reductions of polynomials. And of course, whatever the outcome of the polynomial reduction will be, it's gonna be dependent on the monomial ordering you fixed. Okay, because again, in the univariate case, things are nice because we have an Archimedean ring and the division is well defined. But in the multivariate case, we lose this property and we need to fix ordering on the monomials for the polynomial reduction to be performed. Okay. So the set gamma D defines a subregion of Zn over the rationals, satisfying two conditions. Gamma as a monomial has to be less than or equal 0. This is a monomial ordering. And the second one, gamma plus D has to be greater than or equal 0. Why? Because I need, at the end of the day, when I will instantiate the indeterminate multi-degree D to something, I need to find a polynomial at the end of the day, okay? Because I'm interested in polynomials. So this is why these two conditions are needed. So the first condition says that, so this first condition here says that x to the power d is the leader of the formal polynomial. And the second condition makes the formal polynomial a standard polynomial as soon as the multi-degree d is fixed. Okay? So what can we say about those formal polynomials? Let's maybe just see an example. So here is a two-dimensional example. I fixed a monomial ordering with those independent weights, square root of 2 and 1. I'm going to mention later why I need square root of 2 and 1. I could have chosen like a maybe simpler weights for the monomial orders, but let's forget about it for now. So the picture you're seeing here, so this is, it's not centered as 0. This is d1, d2. This is something called d1, d2. It's an indeterminate. And what you're seeing, those blue dots here, are all the potential exponents of the formal polynomial. Okay, so x to the power d is the leader. This is the leader. Okay, and I don't know the 0 where the 0 is because I don't know d1 and d2. So potentially all those blue dots, and actually many more here that I'm not representing, are part of the formal polynomial I just presented earlier. We do have two nice properties when we start playing with those formal polynomials. The first one is that we have a stability by differentiation. So if we have a delta, or so if we have a polynomial derivation and we take a formal polynomial p, computing d of p, so this d of p here is a formal polynomial. So it's a stable. And the reason for it is rather simple, right? So this d of p is nothing but a scalar product. So it's gonna take the gradient of p multiply f being the vector of polynomials defining the derivation. So it's kind of intuitive why this is a formal polynomial. The next one is less obvious, which is the red one here. It's the reduction. So when we reduce the derivative of p, here, which p again is a formal polynomial, and actually from now on it's going to be always a formal polynomial in the remaining of the talk. If I perform the reduction of d of p with respect to p, okay, so I find some sort of quotient q plus a remainder r, and r again will be the normal form of the derivation of p. It's a standard polynomial. Okay, so there exists a unique standard polynomial, which is r. Okay, such that satisfy this this condition of dp is equal qp plus r. Okay, and so here what this says is whenever you start reducing d of p with respect to p, you are going to find two objects. So one is q. Okay, q, let's say this is not really equal. So q is the quotient, okay, of this division. But the quotient, what the proposition says, that the quotient is a standard polynomial. It's not formal polynomial. So it's really something the usual polynomials we play with. And the second object is the remainder of the normal form of d of p. So this is, let's call it the remainder to make it quick. But this one is formal, okay? So the remainder when I perform this reduction is formal, but the quotient q is not, okay? It's a standard, and this property is quite nice. And we are going to actually have more to say about the support of this quotient q when p is a Darboux polynomial. So the next proposition provides a quite nice over-approximation of the support of the cofactor of the polynomial, of the formal polynomial p. So again, the proposition says if we have a derivation, so if we have a derivation here, and we take p any polynomial, right? if we suppose that P is a Darboux polynomial for the derivation we've fixed, then we know that the support of the cofactor is included in this polytop here that I'm going to define right now. It's called the derivation polytop, intersects the non-negative integers. Okay, this is non-trivial. It has been proven twice. So Guillaume Chaise proved this in the 60s in different contexts. And we provided a proof and using convex optimization in the previous years, like 2 years ago, with Maxime. Okay, so let's say Ghorbal and Brideau. And 24. And let me just give an example to explain what's the derivation polytop and how or what does it mean for the support of G to be well understood. So let's take here this is an example. It's the nice usual van der Pol oscillator. I'm giving you the derivation here at the bottom of the slides. So first of all, I'm going to define this derivation polytop here. So the derivation polytop takes the polynomials defining the derivation and draws a polytop. How? So it first takes y, so here y. So y is supposedly, so x equals 0 and y, it's here. But since it's the derivative with respect to x, you shift it left. Okay, and you find this polytop here. Now, I should have taken green, but that's fine. Now, for the second polynomial here, you just take each monomial. So each monomial represents a dot, and then you shift it down. You shift it downwards because of the derivation with respect to y, and you will find out if you do this that it's gonna be this triangle here. Okay. So in general, each fi will give you a polytop, and what you do at the end of the day is you just take the convex, you convexify all the polytops you found. Okay, this is what I did here. And this defines what's called the derivation polytop, this calligraphic D for a given derivation. Okay, now what this proposition says that in fact, it gives the support of the cofactor. If P is Darboux, it says that you don't care what P is, its cofactor, the support of the cofactor, it's going to be in here, the intersection of the derivation polytop and the non-negative integers. And this is very nice because it gives you right away, without doing any computation, an over-approximation of the support of the cofactor if such a polynomial exists. For Shimizu-Morioka system, the system I presented earlier at the beginning of the talk, this is going to be 3-dimensional, and of course in high dimensions it's going to be high dimensions, but those are 3D polytops. We can play around, we can enumerate the points within, etc., etc. So what's interesting about this whole story of using formal polynomials and using the fact that the cofactor has a over-approximation of its supports is this is the main necessary condition that I'm going to not necessarily read here, especially that we have been already advanced in the talk, but I'll rather present it. So I read it first just to make things more formal. But then I'm going to again give an example to better appreciate how we are going to be using it. So it actually gives necessary conditions on the coefficients of the formal polynomial P and its degree, because this is the main interest of the whole story, such that P is a Darboux polynomial. Okay. So if there is one message to take away from this talk is going to be the following. In fact, we have means to derive necessary conditions on the degree of the formal polynomial P for it to be a Darboux polynomial for the derivation. And this is something completely new with respect to the all other methods, because they do not know how the or what are the necessary conditions for the multi-degree D to be a Darboux polynomial. Okay. This is what this proposition, or actually theorem, says. And if we move on to one particular example, and I'm going to play around with the van der Pol because it's easy to see what's happening. We can actually compute the coefficient of the normal form of the derivation. So this is here the main objects of interest now. So I'm giving a formal polynomial P. I have the derivation D defined by the van der Pol oscillator, and this is what's the complicated expression Cij here is the coefficient of the monomial x1 to power e and x2 to power j of the normal form of dp with respect to p. Okay. And as the previous proposition says, it's going to be some sort of horrible polynomial that includes the coefficients of the formal polynomial, potentially the degree. So you can see actually those here are the coefficients of the formal polynomial p. But what's interesting is you will find here D2, and D2 is actually one of the multi-degrees that I know nothing about for now, okay? So you kind of combine the coefficients with the multi-degree for P to be a Darboux polynomial, and that's what's gonna be interesting. So one way to represent this horrible expression is using just some sort of a nice pattern, which is given in blue here. And how to read this pattern is actually the monomial x1 to the power e, x2 to the power g of the normal form has different contributions from the formal polynomial p, and those contributions are just given by arrows flowing this way. Okay. This is just one way to represent the expression that you are seeing on the left-hand side. And for p to be Darboux polynomial, a necessary and sufficient condition is that Cij has to be equal 0 for all I and all j. Okay, because if for all I and all j, Cij is equal 0, this actually means that dp minus qp is equal 0. And if dp minus qp is equal 0, bingo, we have a Darboux polynomial. Okay. But how can we actually solve a system with infinitely many equations? Because this is the case. There are infinitely many I and j here. So what are we going to do about this? So let me just depict a picture. So this is a formal polynomial. What you're seeing, those dots here, so this area, all this area here, it's sort of bounded, but actually, I mean, formally speaking, it's not. So all the stuff in here is what's called the formal polynomial p. This is, again, x to the power d. This is the leader. And I removed one dot here just because using the fact that the support of the cofactor is bounded. But let's put this aside for now. And I just mentioned this blue pattern that gives a way to actually see what's going on for the normal form of d of p. So, of course, if you put this blue pattern completely outside the formal polynomial p, you're gonna basically find 0 equals 0. So it's not informative. It's not giving you any extra information you can play with, okay? On the contrary, is this blue pattern is completely inside, you're gonna probably find it's not probably, actually, exactly, you're gonna find one equation, okay? But this equation will have this as unknown, this is unknown, this is unknown, probably this as well, and eventually some d1 and d2, okay? So you're gonna one equation, but with many unknowns to be determined, which is not necessarily useful if we are trying to solve the system. But if you are smart enough and you position this blue pattern in a way that just one stuff and exactly one coefficient of p in this case appears, then you will find one equation for one coefficient of p that you can play with and eventually solve. Okay. And for the van der Pol oscillator, actually, this works because by moving this blue pattern in such a way, we are going to find out that, in fact, this coefficient of P has to be equal 0. And if you move it upward, the next coefficient of P is to be equal 0, and then you're gonna play a game and actually propagate this blue pattern all the way, the form of P, and you can actually basically you're trimming the overall shape that you've allowed before in order for P again, this formal polynomial, to be Darboux. Okay, so you play this game, you put the blue pattern, and you're gonna find, oh, this coefficient is 0. Okay, fine. So P is simplified. And this coefficient is 0. Fine. This is simplified again and again and again and again. So you basically end up having, well, you started with something that has a rather generic form, and you end up with something that has basically sort of, the faces of this blue pattern that fixes things out. Okay? And now what to do next, right? So you've played with the blue pattern, you've positioned in a way that have just one unknown for one coefficient, but now you cannot do this anymore because you've played already this game. But we have this monic because the formal polynomials are always considered monic. So x to the power d, which is the leader monomial of the formal polynomial, has coefficient 1, okay? So this is why I'm putting the 1 in black here, because this dot here represents x to the power d. And now again, if you put this blue pattern in a nice way, you're gonna find out that actually the coefficient of P in here has to be exactly D1. You can actually play this game and move the blue pattern all the way up, and you're gonna probably find that this one has to be D1 square, etc., D1 over 4, etc., etc. I won't be doing it in here, but I'm going to comment later on about this possible way to go. You can actually propagate this one downwards, and you're gonna find out that this coefficient of P has to be equal D2. And if now you position the blue pattern exactly here, as shown in the figure, you are going to actually notice that those are going to vanish. So actually this one here, this one here, and this one here are going to vanish. So basically it removes these two arrows, okay? So you're gonna find out in here, this coefficient here, right, has to be some sort of equation involving D1 and D2, which are again the multi-degree that you know nothing about. And it turns out that this one actually is going to be D1 plus D2 equals 0. So for P to be Darboux polynomial for the van der Pol oscillator, the leader monomial, which has the multi-degree D1, D2, has to satisfy D1 plus D2 equals 0, which actually implies that D1 equals D2 equals 0 because those are supposed to be non-negative integers, which actually means that the only Darboux polynomial for the van der Pol oscillator is the constant, okay? Which gives you basically, it's not informative in the sense that the constant, the invariant region is either the entire space or nothing at all, okay? So this is the game we are going to play, but there are challenges because of course here we are visualizing everything. We can play this game, we see the blue pattern, we know how to position it. It's a 2D system, etc., etc. So in general, for this idea to work, there are challenges. Of course, I mentioned the monomial ordering. It's very important because every reduction is dependent on the monomial ordering. And there is the propagation. So here I played it smart and I moved the blue pattern along the support of the formal polynomial P because basically I'm visualizing everything. So I can kind of cheat and say, well, if I put it here, it's probably gonna give me something, etc., etc. And 3D and more, well, you lose this way to think, and we need to find means to propagate properly without visualizing things. And the last point here is, so what if there exist actually Darboux polynomials for the system? So what will be, how can we use those necessary conditions on the multi-degree to find or generate Darboux polynomials in faster ways? So we do have for now let's say partial answers for the monomial ordering. We do also have partial answers for the preferred directions, which I'm going to mention next. And actually, Maxime played around a lot with making the current generation algorithms faster by using those necessary conditions, but I'm not going to delve into the details of this in this talk, okay? So for the monomial order, I will just say one thing. In fact, if we use a weight with irrational numbers, it has a nice property that the hyperplanes defined by this total weight will just touch one integer at a time. Okay, so if you think of, let's say, if I go to probably this picture, I can explain it better. Yeah. So if because here the weight is square root of 2, 1. So actually this defines an order on the entire system, and the order looks this way. So you have a hyperplane, in fact. You have a hyperplane, and well, of course, my picture is not good because square root of 2 is actually more like so. And this is going to be this vector, the normal vector of this hyperplane is square root of 2, 1. Okay. So if you take this hyperplane and you move it, you basically sweeping this entire one, you're going to touch one point at a time because you have used rationally independent weights. And this actually order the monomial. So if you touch this one first, it's going to be your first. You're probably going to touch this one second, maybe this one third, maybe this one fourth, etc., etc. And this gives you an order of the monomials. And the fact that you touch just one at a time gives us a nice property for the propagation later. Of course, if you use weights, let's say 2, 3, or 1, 1, etc., you may touch many monomials at once, and it actually makes the equations we're propagating later on harder to solve in general. Okay. Now let me go back here to my challenges. Okay, so this is my comment about the monomial ordering here. So now about the propagation. So are there preferred directions? And actually, we think that there are preferred directions. And let me explain this on an example. So this picture here gives a plot for the formal polynomial in 3D with some particular, of course, I needed to fix d to something in order to have the picture. But if you want, if you think of this one here as x to the power d, you can move on in every other direction, and it's going to be to define your formal polynomial. Okay. So what I'm going to say here is that if you start in xd and you move on the surface, like on one of the surfaces of this polytope, we are going to find some nice recurrence relation on the coefficient of the formal polynomial p for it to be Darboux for the derivation we've considered. And I'm going to give an example and probably end the presentation here to give you some time for questions. So now I'm going back to the Shimizu-Morioka system. Okay. And I will be playing with this monomial ordering here. So those are rationally independent elements, as I said before. And I will consider the sequence I will call UK, which is going to be about particular coefficients of the formal polynomial p. So those are, again, coefficients of the formal polynomial p that I know nothing about. I don't know what d1 is. I don't know what d2 is. I don't know what d3 is. I don't know what this coefficient is. All I know is I have a recurrence relation to satisfy, okay, because I just actually positioned my blue pattern. Of course, the blue pattern is not the same. It's given by the system I am trying to analyze in order to move along those dots in here, okay? So I'm moving along the surface in a very particular way. And actually, this gives me that I have a nice recurrence relation, okay? So if I just multiply everything out, so I take u1, 2u1 multiply 4u2 multiply, so 2u1, sorry. I take the I'm gonna take the product of everything in here, take the product of everything, of course, make it equal and take the product. It's going to give me 2 to the factorial k uk equals something in d2 u0. So again, I will not stress enough the fact that d2 here appears in the recurrence relation, and this is something I do know, I do want to characterize, I do want to understand better how those coefficients behave for P to be Darboux, okay?
Okay, can we quickly wrap up because
Yeah,
some people have to
definitely,
attend
definitely.
other meetings also. Yeah, sorry for that.
Absolutely. So, this is going to give me a condition, and this condition is going to using this condition actually we will be able to find out that d2, the degree I know nothing about, has to be even. Okay. Moving on, I can also find out that actually d1 is equal to 0. Okay, so now I know that d2 has to be even, d1 has to be equal 0, and further on, I can find out that d3 actually always has to be equal 0, always has to be equal 0 for every even d2, okay? Therefore, the theorem says that the Shimizu-Morioka model has no non-trivial Darboux polynomial like the Van der Pol oscillator, and we've been able actually to analyze many systems like so, and even general systems like linear systems, to say that they don't have Darboux polynomials based on such analysis and finding out necessary conditions for the multi-degree D to be satisfied. So the conclusion and wrapping up, the main thing I presented is the concept of formal polynomial and how to use it. It actually gives a uniform framework to automate the reasoning about Darboux polynomials and gives relevant necessary conditions for the generation procedures, and actively ongoing try to formalize those recurrence relations I mentioned for the Shimizu-Morioka systems. Thank you very much, and indeed, I'm sorry because I just drifted a bit for the time. So if you have any questions, please feel free to answer. Feel free to ask your questions. I'll be more than happy to explain or actually try to answer the questions.
Okay, great. Thank you very much for this very nice and interesting talk. As a compromise, for technical reason, I suggest we stop the recording here and have some questions unfortunately, without recording. Is that okay?
It's okay for me.